Current aerial designs predominantly feature one-joint wing systems to enhance diving speed while managing vibration and mechanical durability. Inspired by the double-joint sweep wing morphology of the peregrine falcon, our project examines how this design affects vibration and speed during diving. The aim of our research is to test whether a two-joint variable sweep wing system that folds its outer wings toward the body during flight can increase diving speed and reduce vibrations compared to fixed wing and one-joint wing configurations. Our team designed and manufactured this aircraft that is capable of achieving zero-joint, single-joint, and double-joint actuations. This design minimizes the possibility of confounding variables by testing it all on one aircraft. The wing assembly consists of 9 components: 2 outer wings, 2 inner wings, 1 base wing, and 4 torsion springs. The design has 2 core mechanisms. The joint mechanism employs a quarter-circle guide rail for a rotational hinge motion, and also has torsional springs for retraction to fixed wing position. A spool mechanism on the back of the plane connects to both outer wings with 2 strings. The pulley is connected to a motor underneath, so when the motor is actuated, the pulley retracts the outer wings and cycles through the 3 morphing stages. As for our electronics, we have our vibration sensors carefully wired and taped underneath the wing. Also taped to the side of the fuselage is an SD card data logger module, which is responsible for collecting real-time sensor data. Underneath the fuselage is our power switch connected between our battery and barrel jack. Once we open the fuselage, we have our 9-volt battery, which is supplying power to our Arduino Nano, which is then down-regulating it to 5 volts. The 5 volts of power are then being distributed via a PCB board, which in turn delivers the power to each component. The components are connected to the Arduino Nano via signal pins, with the exception of the FS90 servo. On board the plane, we have a BM390 altimeter sensor that is connected to the Arduino Nano. As for our servo, that is connected to our receiver, which communicates wirelessly with our transmitter. For our experimentation, we launched the glider at a consistent height of 130.5 inches across 5 trials. This was done for each wing configuration for 15 trials in total. Motion capture techniques were then employed, utilizing tracker video analysis and modeling tool to derive positional data for a velocity calculation. Finally, data analysis was performed by utilizing Excel, Python, and MATLAB. To process our results, we used the time intervals taken from the motion capture data to get the average vibration during diving. We used that same time interval to get the average velocity during diving as well. However, when running the ANOVA post hoc analysis, we realized that the standard deviation was too high and the data we collected would not be statistically significant. So we decided to smooth the results by graphing the average velocity by time percentile. Once both of our datasets were statistically significant, we ran a one-tailed unpaired t-test. The results suggest that the double joint and single joint wings have the same amount of vibration, which was greater than zero joint wings. For speed, the data shows us that the double joint wings average higher velocities than both single and zero joint wings. Our findings highlight a promising breakthrough in the design of unmanned aerial vehicles, offering innovative solutions for enhanced aerodynamic performance.